stress distribution in concrete structure. In 1930, an American civil engineer, Charles Whitney, developed an interesting approach to calculate the stress distribution in compressive part of a concrete block. He just replaced the tough parabolic distribution of stress in concrete part with a far simpler approach of a rectangular stress distribution. Charles Whitney, from late 19th centuries to mid 20th century, and one of his unique work is Lincoln Park Bridge design in Kenosha, Wisconsin. What he did, he just replaced this is the actual block of concrete, this is the actual one, and this is the compressive part of that compressive stress distribution. And if we just say that this is C, this is the distance to neutral line or axis, this is neutral line or axis, and this is the actual distribution, this is the actual distribution of stresses, which is the parabolic distribution. And definitely at the bottom there is a tensile part of steel rebars. These are steel rebars embedded in concrete, steel rebars, and that's a tensile force equal to area of steels time a force of Fs. We'll talk about that later. And this is the compressive part. He just replaced that with a equivalent section, and in that equivalent section, he just replaced the parabolic distribution with a rectangular. The whole point is to calculate the height of this rectangular distribution. A is definitely a portion. Again, this is C, and A is a portion of C. So if we call this is definitely, let's make it a bit cleaner. So if the compressive force in the actual case, in the actual one is, let's say this is alpha times F prime C, coefficient times a specific strength of concrete at the top. So for example, if the equivalent is gamma F prime C, those are just coefficient times the specific strength of specific compressive strength of concrete. So for they have a coefficient for themselves, so that's a alpha F prime C, a coefficient times the specific compressive strength times C, distance to neutral axis, times the other dimension, which is B. So that's the area. And for the equivalent one, that's gamma F prime C. Compressive force is gamma F prime C times A height times B, again the direction to the board. And these two should be equal to each other because this is the real and this is the actual and this is the equivalent. So in that case, and again, F prime C is a specific compressive strength of concrete. So for example, if the resultant force applied at a distance of beta times the distance to neutral line at both, so this time for rectangular section, this is A over 2. So A over 2, half of the rectangle height should be equal to beta times C because resultant should apply at the same point for both of them. In that case, and also we do know C is a portion of distance to centroid. Definitely A is smaller than C. C is all the way to here, but A is something like maybe 80% of that, whatever. So that's beta 1 times C, a coefficient times distance to centroid. So if again we call this equation 1 for actual and we call the equation compressive force for a rectangle equivalent one, equation 2, they should be equal to each other. And if you make them equal to each other, it just gives you gamma gamma is equal to alpha over times C over A. Mhm. And at the same time, we do know A, the height of rectangular block, is a percentile of distance to the neutral line. So A is beta 1 times C. If you replace it in the equation, it says gamma is equal to alpha over beta 1. And all this coefficient for calculation, the height of A finally. So eventually we get there. So from the other part, A over 2 is equal to B over C. B times C is the equation of resultant force from the top of the section at both equivalent and actual case. So A over 2 is beta times C. So it says A is equal to 2 times beta times C. And from the other equation, A is equal to beta 1. So it just gives us beta 1 is equal to time twice of beta. If we look at this table gives us a range for compressive strength of concrete. So that you can easily see for the concrete with the F prime C less than 4,000 pound square inches, we have alpha, beta 1, and a gamma. And likewise for 5,000, 6,000, 7,000, and bigger than 8,000. And you can see easily that the gamma is not varying anymore from 86, even from 8,000, probably 40,000. So even for very strong concretes. So one can easily say for most of the case, gamma can be replaced by 85% because it just make a average base of them and it just gives us 85 because they are three of them are 85, so it just gives us a weight average, gives us a gamma of 85 times F prime C, that's a compressive force for the top, and gamma F prime C times A, which is a constant times the coefficient times distance to neutral line, and say that beta times beta 1 times C or beta times X. C or X is just distance to from the top of the section to neutral line or axis. You can use either of these. So it just says it seems that the intensity factor for compressive strength gamma is essentially independent from F prime C. So you can just replace 85% the concrete compression force at failure in rectangular beam. Its of B is this equation. So if we do know A is this one, 2 is this one, and also gamma from the previous slide can easily replace by a 0.85. So in that case, 0.85. If that's 0.85, in a balanced strain condition, it just says then Fs goes to Fy. When the tensile part in down at the rebar goes to yield, that's Fy. The stress for steel rebars. So and for the whole cross section, summation of forces in x direction, it just says tensile stress should be equal to compressive stress. And if you apply that for one which uses this coefficient of gamma 0.85, it just says 85 times F prime C. 85 times F prime C is times A times B is equal to tensile force, which is area of steel times yield stress of steel. If you calculate that based off A, distance or height of rectangular distribution, that's simply A is equal to area of steel times yield stress of steel over gamma times F prime C times the other dimension of the section. That's all they need to for calculation to the height of equivalent uh, you know, rectangular distribution of stress, and that's very useful. We'll solve more problem on this on next video. Thank you.